Hi, welcome to my channel EduTech. Today we are going to discuss one more topic, transition capacitance from diode capacitance. Already we had discussed in my video as diffusion capacitance. Now today we are going to cover transition capacitance. Okay, so now let's talk about transition capacitance. As we know that this transition capacitance which is working under reverse bias condition. What is mean that? Transition capacitance which is working under reverse bias condition. Why? Because just talk about what is capacitance. Thereafter you should know why I am comparing this transition capacitance as reverse bias condition. Just take capacitance symbol like this, and these two parallel plate capacitor which is two are conducting parallel plate capacitors. So these are the conducting materials. Okay, so this is plate 1 and this is plate 2. In between we are placing as to fill this gap between these two conductors, that is dielectric material. Dielectric material, or you can say insulating material. This gap which is going to filled by dielectric material or insulating material. So there is some gap. So this is nothing but capacitance. Okay. So generally this capacitor which is used to store the electric field. Okay. And also this capacitor which is used in amplification like bypass capacitor, coupling capacitors. Okay. So different applications which are used as these capacitors. But now we are talking about transition capacitance. Okay, so it has two conducting materials. In between the gap is filled by dielectric or insulating material. Now just look at this capacitance which is similar to the operation of reverse bias condition as PN junction diode. Now let me draw the diagram. So this is P type and this is N type. This gap represent depletion layer. Depletion layer, or we can say that space charge region. Hope you understand. Now between these both materials which are connecting as supply like this. Okay, now which is connected as this one is reverse bias. For P type is connected to the negative terminal, for N type is connected to the positive terminal. Okay, P type is connected to negative terminal and N type is connected to the positive terminal. These voltages which are represent VR. Okay, and this is the width of the depletion layer, that is W. In between of these two layers, that is P type and N type, there is a immobile ions which are present. Immobile ions. Okay, for P type which are presence of nearby junction is negative, and N type nearby junction which are presence of positive. Okay, that is holes. So this is nothing but junction. In this junction has depletion areas, we can represent width. Okay, so this is reverse bias condition. Now just look at this capacitance and this reverse bias of PN junction. This is two conducting materials. Similarly, look at in PN junction of reverse bias, this is P type conducting material and this is N type conducting material. Okay, and in between across the junction there is a depletion layer, and this depletion layer width is W. So just look at conducting material of this plate and this conducting material of this plate, both are comparing equal. At the same time, this capacitor between these two parallel plate capacitor, there is a filled, right? There is a gap. That gap is filled by dielectric material for capacitor. Similarly, this P type and N type has in between there is a depletion layer. So this is perfectly suited by the under reverse bias condition. So here how the current will be reduced in the sense. So here this is nothing but a reverse bias condition. So all these holes which are going to attract with negative terminal, all these electrons going to attract with positive terminal. So here because of these charge carriers are going to attract with this potential battery, what will happen means, so here there is no reducing forward current because we were connected as reverse bias condition, so that here low current will reduce. So but there is some amount of current is produced. That current is due to magnetic charge carriers. That current is called reverse saturation current. Reverse saturation current, that is due to magnetic charge carriers. Due to minority charge carriers. Because of this charge carriers, the current will reduced. Okay, that current is reverse saturation current. That is represented as I0. Okay, so now due to change of charge with respect to change in voltage, that is CT equal to dq by dV. Now we need to find out the transition capacitance epsilon A by W. Okay, so this is the final expression. We need to prove the equation of transition capacitance. Okay, now if we want to prove this equation, in the sense we require some relation between potential and charge density. With help of that equation we found this final expression. Let me start the derivation of transition capacitance to prove this final equation. So I need to prove that equation means I need to take the relationship between the potential and charge density. Is given by Poisson's equation. Poisson's equation is, so what is the Poisson's equation? D square V by dx square, that equal to QNA divided by epsilon. This is the equations which are taking under Poisson's equations. So d square V by dx square is equal to QNA by epsilon, where Q is nothing but charge, where Na is nothing but acceptance ions in the p type, and epsilon, where epsilon is the equal to epsilon naught into epsilon r. So where epsilon naught is nothing but what? Epsilon naught is equal to permittivity of the free space. Permittivity of the free space, that is what? Epsilon naught. That epsilon naught equal to 1 by 36 pi into 10 power of 9, that equal to 8.849 into 10 power of 12 minus 12 farads per meter. So this is the value of the epsilon naught. Okay, where epsilon r equal to relative permittivity of the semiconductor. Relative permittivity of the semiconductor, right? So this is nothing but epsilon r. Generally we are taking these kind of values in the sense when we going for derivative for respective topics, these are the values are supported to derive the equations, so that in this we are going to find out the value of transition capacitance across the junction. What is the width if change in charge with respect to change in voltage in the semiconductor PN junction diode? So that we have to use these equations. Okay, right. Further, look at this equation. Let us consider equation 1. Okay, now from equation 1 I am going to integrating. Why I am going to integrate? Because from this value I need to find out voltage. So that integrating on both sides with respect to x twice from equation 1. Hope you understand. So from equation, Poisson's equation, I am going to integrating on both sides with respect to x from equation 1. So what we do? Integral d square v by dx square into dx, that equal to integral qna divided by epsilon into dx. If you integrate this expression, what will get it? One time integration is happen, that is dv by dx, that equal to q into na by epsilon. This will get into the same. Then integration dx x. Okay. So after one time integration is happen, you will get this expression. Now look at further derivation. So again we need to integrate, because from equation 1 what I said, we need to integrate twice. Okay, so we need to integrate twice, so that first time is completed. Now second time again I am going to integrate. Again integrate with respect to x in above equation. In above equation, what we get? Integral dv by dx into dx, that equal to integral qna by epsilon into x into dx. Now, so integration differentiation get cancelled, in the sense what is remaining? V. So v equal to q into na by epsilon into integration x means, as you know, x square by 2. Okay, that is the value of after integration with respect to x. Then what will get? From this expression, v equal to qna by epsilon into x square by 2. So I can written as like this: q into na by 2 epsilon, these two get into the here, so into x square. Now we need to draw the diagram for p type and n type. This is p type and this is n type. Now just small analysis. So here this is the p type and n type, right? This is lightly doped, this is lightly doped, and this is highly doped. Highly doped, because we considered some examples like abrupt junction or ally junction or ally junction. So in this case, this is both materials are not equal. Okay, both materials are not equal. So p type is lightly doped and n type is heavily doped. Okay, so in this region, so the depletion layer, so whenever this lightly doped is happen, that is low concentration is happen, so the depletion layer becomes high in this, the width is very high in p type, and n type depletion layer is very low because this is highly doped, so that it look like this. The width is very small in the case of n type, and the w width is high in the case of lightly doped, so that you need to, from this point x is equal to 0, and when increasing this depletion layer from this point to this point, that is x is equal to w. So I'm going to consider this total distance density from here to here, that is x. X is measured with respect to junction. So that's why I'm going to take for, let us consider x is equal to w and v equal to vb, because this is when a reverse bias condition, there is a width is increases, depletion layer increases, so that the electric field intensity of voltage is across the junction, so that where v can be written as vb and x is equal to w. With help of these values, I am going to replace this above expression. What is that? vb that equal to v can be replaced vb and then q into, that is q into Na by epsilon into 2 into, in place of x, that is can be written as w square. Okay, see, when variable potential increases, width increases. When it's happen? When reverse bias condition. When reverse bias condition, the depletion layer increases, then the width of the depletion layer also increases. So w is directly proportional to vb. W square also can be written as w directly proportional to square root of vb. Okay, it's all about due to reverse bias voltage. Okay, now further this equation I am going to consider equation 2. Right, now from equation 2 differentiation with respect to voltage from equation 2, right, we get, what is the equation? V equal to, see, vb equal to qNA by epsilon 2 into w square. Now I am going to differentiation with respect vb, that is voltage. So what is the expression becomes? dvb by dv. See, v means vb now, so that I can write as directly, that equal to d by dv into q Na by epsilon 2 epsilon into w square. So this is the differentiation with respect to v. I am going to derive. So what is that? So dv by dv, that means dvb by dv, that equal to qNA by 2 epsilon into d by dv w square. So this get cancelled, 1, that is q into Na by 2 epsilon. Now differentiation with respect to v annappudu, then d w by dv into 2w. Okay, so after differentiation with respect to v, so you will get like this. So now here 2 get cancelled, that is qNA by epsilon into w dw by dv. Now in further simplifications, this equation I am going to prove, that is dw by dv equal to, what is the expression becomes? This epsilon get into the numerator in LHS, that is epsilon by remaining values qNA into w, that is qNA w. This is considered equation 3. Okay, now we got this expression. In future this equation is going to substitute, so that I have written this equation from above equation. Now q equal to, that is number of charged particles into charge of each particles. So what is charge? Q is nothing but charge, that is Q equal to number of charged particles into charge of each particles. So just look at here. So this is the junction, right? W, this is P and this is N. So this total area is nothing but magnetic charge carriers. So when you are applying reverse bias condition between P type and N type, due to reverse bias voltage is changes, the charge will get changes. Okay, in that this is the total area. So total area is nothing but, so this is the P type and N type. This is the depletion layer total area. Okay, so in this area nothing but area of cross section. So in this area what are the things are there? Minority charge carriers. So particles of charge carriers, that is what? Q equal to number of charged particles, that is Na into volume. So number of charged particles is nothing but Na into volume into charge of each particles, that is Q. So we are talking about what? Transition capacitance. In transition capacitance, that is across the junction there is a depletion layer is maximum. If depletion layer is maximum, that is W is high due to reverse bias condition, so the magnetic charge carriers are having, that is Q equal to Na into this volume can be written as W into A into this Q, right? So what is volume here? Volume is nothing but A, W into A, where A is nothing but cross section of area at the junction and W is the width. This total width having total area. In this total area only charge is there. Charge means charge carriers. Okay, so for that relation we have considered Q equal to Na into W into A into Q. So this is equation, let us consider 4. Okay, so I am going to differentiating with respect to V from equation 4. Differentiating with respect to V from equation 4. What we get? dq by dV, that equal to d by dV into Na into W into A into Q, right? So this is the equation. dq by dV equal to d by dV into Q, Na into W into A into Q. Okay, now I am going to differentiate with respect to V in this equation. So what is the expression becomes? dq by dV, that equal to Q into, that is Na into W into A into Q na. I repeat once again, d by dV. So dq by dV equal to, now Na into, I have written like this, A into Q into dW by dV, because what I said previous, width is directly proportional to square root of VB, right? So voltage changes, width changes. If width changes, barrel potential, depletion layer barrel potential increases. So that for that relation, this is the equation we have to write. Okay, so from this expression, dq by dV, that equal to Na into A into Q into dW by dV. What is dW by dV? Look at from equation 3. I'll tell you equation. I'll show you equation 3. So this is the equation 3. dW by dV equal to epsilon by Q Na into W. Okay, now this equation we are going to substitute from equation 3. Right? So in place of dW by dV, that is epsilon by Q into Na into W. This is the equation from equation 3. Okay, now Na cancel, Q cancel. What is the remaining equation? dQ by dV equal to epsilon into A divided by W. Look at from equation 3 we have to write, because we need to change this value, right? So that from equation 3, so dQ by dV equal to, this is the equation. After cancellation, the final equation is dQ by dV equal to epsilon A by W. Okay, now in initial equation, what is transition capacitance? CT equal to dQ by dV, that equal to, what is the expression? Epsilon A by W. So the final expression is CT equal to epsilon A by W. Okay, so this is the transition capacitance expression. Okay, where CT is the transition capacitance, where epsilon is the permittivity and A is the area of the junction. So this is the area of the cross section of junction. Okay, then W, that is the width of this depletion layer. So that is the relation of transition capacitance. So this is what transition capacitance derivation part. So thank you for watching my video.